Good morning, everyone. Today is December 7th, 2019, and this is the John Chappell Natural Philosophy Society Science Chat. So let's see who we got in the live room. We've got Ian in the live room today. Good morning, Ian, or afternoon to you.
Yes, morning, afternoon. You're a little faint, actually, today, Franklin.
My volume is a little bit faint.
It was a little, yeah, yes.
Is it okay now? Maybe it wasn't
It's
just
a bit better. It's a little fainter than usual, but it's better than it was a moment ago.
okay. Well, I am using my headphone here, and sometimes I find that the headphone doesn't work as well as just the regular PC microphone. But as long as you can hear me, I think that's okay. Well, glad to see you're here. Because you're the only person in the live room. I think Dr. Lucas is sent a message from YouTube, so maybe he's hanging out at YouTube. Of course, Dr. Lucas, I would invite you to come to the live channel here, since there aren't too many folks here uh, this this morning. So yeah, so if anyone would like to come to the live room, you can do that and participate. So Ian, is there something on your mind that's been going on this week?
Yes, I'll come to that in a second, Franklin. Just maybe mention quickly before anybody is here, really. Um, Following my participation in the conference held by David some weeks ago, I sent him an email with, I don't know, about half a dozen attachments, suggesting that he might update the wiki and scientists database. I also actually succeeded, I think, in joining the CNPS, which I hadn't succeeded in doing. It seemed to want me to register, which I did, and I think I sent $36 or something. But I've received nothing back on either account, so I just thought I might mention that to you.
Okay.
For example, with my wiki entry on the database and in the wiki, it gives my former work address and email, which are no longer extant because I've retired, nearly 3 years ago. And some of the things are out of date, and I gave some extra things. So I don't know if David is looking at that or what. Haven't heard back from him.
Oh, I suppose you could always send him an email. He's usually fairly responsive about things like that.
Yeah, I don't know if he received my earlier email because he didn't acknowledge it. I was having some difficulty with emails, so that's one thing.
Well, you might want to try again.
Yeah,
He
okay.
probably gets a lot of emails, and he might not immediately recognize. Because I don't know how people handle, when you get like a zillion emails a day.
I know.
You've got to like ignore, some large fraction of them.
And I have email-free days. I mean, I decide maybe for a day or two just not to log in. So people say, have you not read this? I said, well, I haven't been in my email for 2 days, so I don't know.
Yeah, they probably think you're in a ditch or something.
Yeah, think I'm a dinosaur.
Yeah, okay. Well, did you see any interesting science topics coming your way this week?
This week, well,
I think I still saw that there's some discussion about the inability to find dark matter. I don't think we've discussed that particularly.
Yes.
I think I just saw that like Yahoo News.
I was considering again something that I think I've raised once or twice in the past, and it just seems to be neglected by mainstream and so on. That what we look at in the night sky, when we're looking at very distant galaxies and so on, nebulae, is not actually a contemporaneous snapshot. We're really looking at a composite image of all different things that have emitted light a different number of years ago. So, if we're finding some gravitational effects from areas that are dark, there's no visible matter there. Well, that's merely because the light that emanated from matter, which is there, let's say, has either not reached us yet or has bypassed us. I mean, the object has to be the same distance away from us in light years as the time previous to us in years that it emitted the light. If you follow.
Kind of, although I'm not sure that explains, say, the main thing is the galaxy rotational curves, and that the planets or the galaxies all appear to spin at relatively constant rates, which causes the well, at the same speed, right? So I think that kind of actually causes the twisting that we see in galaxies, because the outside uh, suns have to be moving at basically the same speed as the inside suns. So the inside suns can circle around once a lot sooner than the outside ones. And I think that's an interesting reason, maybe, why the galaxies have spirals at all. Have you ever wondered about that?
I have, yes,
why
and
does it look like a bathtub?
my tentative
Thing?
position at the moment would be that they're actually not spiral at all. It's an optical illusion. That they're probably spherical, maybe elliptical, and the combination of the various rotations, maybe about different axes, combined with what I've just said, that we're not viewing the galaxy as an instant snapshot. We're viewing different parts at different times. That gives rise to the spiral nature of the galaxy. I think you can actually do some computer simulations which might give you some spiral arms if you have sort of a spherical object which is rotating, but you're seeing different parts of it at different times. So I think a lot more work could be done on that, but that's my tentative explanation. I think this whole business of spiral galaxies is an optical illusion.
Well, I guess I would find that hard to believe, because I think we've seen in pictures, we can see that the galaxies are more or less flat. I mean, they definitely have a plane to them, and so they could be this way. And if they're facing this way to us, then the light from all across the galaxy would be hitting us at the same time. And so certainly we've seen spiral galaxies that are in that orientation, right? So I mean, if the galaxy was like this way, then it's like the light from over here might take a little bit longer than the light over here. Although for the size of the galaxies we're imaging, I don't think even that would make a huge difference. So I would be surprised if the image of the spiral galaxy wasn't something that was totally real.
But it's not a little bit longer, surely, Franklin, that it's taking. I mean, it could be millions and millions of years. We could be seeing parts which were separated by millions and millions, thousands of millions of years, a difference in time.
But if the galaxy is facing us flat, then the difference would be negligible, right?
It might not be as great, but the apparent flatness might be coming from different areas behind, an imaginary plane there. It could actually be further back.
That's why we have to observe all the other galaxies which are not facing us, so that we can verify that there's actually, because this is the other weird thing about galaxies, is why is it that, I mean, there are some spherical, galaxies, but the large number of them seem to be flat, and especially the ones that have the spiral features are flat. Like we think the Milky Way itself, we've mapped out. You've seen pictures of the Milky Way, and you think that we know what that looks like. However, they do it, and they show us where we are in our spiral arm in the Milky Way as they've mapped it out.
Well, I knew
in our neighborhood, you think that can't be something that we're misobserving.
I'm not quite sure how they determine that we have spiral arms. I mean, when I was growing up, I suppose I learned in school that our galaxy was rather like two plates, one put on top of each other, with a slight hump in the middle, maybe two saucers, yes. And it's only in recent years that I've come to the information that they believe they understand, or they've measured, or they've deduced that we have spiral arms. Now, I'm a little skeptical about that information, and I'd like to know a little more about it.
Well, let's see here. I just did a little Google search on that. So there's our place in the Milky Way galaxy here. So apparently they have this map here. And they've mapped out where these other various things that we see in the sky are. And apparently that's what it looks like, I guess.
I'd possibly put in the same caveat that even within our own galaxy, you're not looking at objects which are contemporaneous. You're looking at some objects which are particular time ago, another maybe lesser time ago, and other areas that are actually at the present time populated, but you can't see them because the light hasn't reached us, or it's bypassed us.
Well, that would be kind of presuming that the lights kind of blink in and out of existence, which is possible.
Well, it's more, yeah, of course, but it's also that the object. I mean, it's hard to explain this now, but if you're say X light years from an object, here's the observer and here's the object. Now, if that object is moving around this area, well, it's only when it actually crosses the position, which is X light years from you, at a time X light years ago, that you'll see the light now. I mean, it could be moving all over the place, could be moving at very high speed, and all you're seeing is that it's actually a coincidence. The coincidence of the position of this object, which is giving off light, at a particular point in time, say X light years away, when it actually crosses the line, which is X light years from us, will we see it? I mean, it could be moving all over the place at great velocities, and we won't see it. It might be at this point, say, in another. Well, say 1 million years ago or something like that, but we won't have seen it at that time. So it's a bit difficult to do without maybe having a whiteboard to indicate to you. But it's a bit of a concept that, funny enough, I'm finding it a bit difficult to explain to people, and which is understandable. But I think you might need a bit of a whiteboard to indicate that. I don't know if I've explained it at all very well, but you see my point about the coincidence. Another example might be if you think of sound. Now, sound obviously travels much slower, but we're talking about shorter distances. So if you hear, say, a clap of thunder from a distant cloud, well, you're actually hearing what emanated from it a time ago. It might be some seconds ago or something like that. That the clap actually occurred. But you're actually also, if you imagine that you're saying, oh, there's the clap up there. It's just given rise to that sound, that thunder clap. But that's what happened some seconds ago. I mean, God knows what's there now. Maybe that's dissipated completely, that thundercloud. Maybe it's another position. It has to be at the position, the same number of light seconds ago as the distance in light seconds from us that it is. I don't know if that makes it any clearer.
Well, I mean, the principle there is quite sound in that if we're looking at some star that's like, a million light years away from us, that we're looking at something that happened a million years ago. It's as if we had like a gigantic telescope to go look at some planet that has some other people on it, and we were to look at them, we'd be seeing what was happening 1 million years ago. God knows what they're doing right now. They could be sending
Right.
spaceships
So,
to us right now, and we would not know it.
so suppose you look at a nebula, the front part of which is a million light years from us, but the rear part of which is 2 million light years from us. Now, what are we looking from? The rear point. Yeah. Okay. So we're seeing a combination of things which happened a million years difference in time. We're not looking at a contemporaneous snapshot, as I say.
Yeah, I mean, I think that's all true, but the question is getting back to, say, the implication that the actual spiral appearance is a result of that. So that's what I would say is under question there, and I still have a hard time understanding how those effects could cause us to view a spiral galaxy, like the pictures I was showing, could cause us to view something like that. I mean, you'd almost have to have a cone-like structure pointing straight at us in order to get such kind of distortion.
Actually, I talked about some simulations or something like that, and I think Kelly claimed to have done some simulations. Maybe the best thing, if you'd give me a moment, I'll just get his book from the bookshelf, and I might show you one or two diagrams. Shall I do that?
It doesn't take too long.
No, it'll only take about 15 seconds. I just have to walk up to the bookshelf. Yeah, I'll do it now.
I see we also have Bob in our live room. So, Bob, if you have any comments about dark matter or the nature of spiral galaxies, I'd be interested in knowing, since the bone of contention here is whether they actually exhibit that spiral format. I suppose that would be one other alternative way of explaining away this dark matter is if we're not correctly tracking the actual speeds in the galaxy.
Sorry, I haven't heard anything you've said in the last half minute or so.
That's okay. I'm just filling time. So.
Oh, okay. I just thought. Okay, let's just see. This may be in some of the papers, but let me see. Can I find something? He has a thing called Wither Galaxies. Now,
but would he also agree with this notion that maybe the spiral galaxies aren't spiral?
Yes, I think so. Now, I don't know if you can see that, but well, the first diagram there is just showing you, sorry, this one here, how you can have a combination of various types of rotation of a galaxy. Now, he says that if you do that, and if you take into account the difference in time, now it's too small to see, but he's talking about a near side and a far side, and a position maybe 50,000 years ago. Well, he says that if you what's happening is it's the axis of rotation is this way. The position 50,000 years ago is maybe front on. The position 25 years ago is we're looking at it just just like that, and the position now is it's maybe in an intermediate position. Now he says if you combine all those, he claims you get that diagram there, this one here.
Well, what is that? That looks like three rings stuck
Yeah,
together.
three rings. Now, then he says, how do you get the spiral from that? Well, they have truncated arms, a feature which has puzzled astronomers. The fact that the arms are curtailed and do not continue to closure is explained here by the requirement that distance in light years must equal the time in years for a light signal to traverse the same distance. As explained above, this requirement is not necessarily met for all parts of a galaxy which is rotating. Consequently, there is a cutoff point beyond which we will not observe anything. If, for example, in if an earlier figure, the cutoff point is at a distance of 60,000 light years. Beyond that, we see nothing. So he claims that you get that, a cutoff point, which gives, sorry, I'm mixing up left and right because I'm looking at the camera. This diagram, this one here. Sorry,
Well,
this.
you might get something like that, I suppose, if it was all mixed up.
Yeah, it's an interesting concept, and for example, he says the hub will appear larger, and the galaxy Messier 100 is of this appearance, with a cutoff and the hub appearing larger.
I mean, that kind of looks like that other picture that I had. Which is like, this is a barred spiral galaxy known as NCG 1300.
Oh, okay, that's you haven't given a Messier number, but you've given the national classification stars. Yeah, okay.
But galaxies come in all sorts of shapes and sizes.
No, that's true.
If I were to Google them, you would see them. So while I wouldn't disagree with the basic principle, I would say that there are certain pictures of galaxies that, generally speaking, cannot be explained by, say, that. Let's see how many images of galaxies we can see. Yes, all different kinds.
I suppose, in a way, my contention would be, I accept all that, but to do an analysis of the rotation velocity of galaxies or spiral arms of galaxies, just by observing a snapshot from a telescope or radio telescope is erroneous, because you're looking at different points of the element at different times, separating by quite significant time differences. I suppose that's what I'm saying. And therefore, this whole business of inventing dark matter. I mean, my idea would be much simpler. I mean, I object in the same way as we all do. We've talked about this many times, about sort of ad hoc hypotheses to save theories, which is really what it is. That's true. But I say that all these gravitational effects, and which cannot be explained ostensibly by Newton's laws and so on, are due to the fact that there's matter there which we cannot see, because it is not the same distance from us at present as the time that it emitted the light, and also we're seeing different parts of the unit at different times. So to do a simple calculation as if it were an orbital system in the solar system, which is basically viewed contemporaneously, is erroneous, and hence the dark matter is a very simple invention to get over that.
Well,
I might call it dark steam, because we don't see it unless it's the same distance from us as the number of years ago that it emitted the light.
So I'm showing you a picture of a spiral galaxy which appears to be face on to us, and there's a number of pictures of galaxies which suggest that these things are flat. So how is it, do you imagine, the actual distances are significantly different to cause this picture to happen? How in your mind do you think that that happens?
Well, that would probably be similar to his example of the spiral galaxy, and I suppose uh, he would say that it's actually rotating this way.
Oh, I can't see what you're doing. But
Sorry, it's rotating about a vertical axis. It's probably an elliptical
this is
type
rotating
galaxy.
on a vertical axis. Okay,
About
so it
yeah,
looks like it's face on, but you think it's actually rotating. It's like on showing you the edge, I guess.
yeah. I suppose in a way, I'm saying that if you imagined, like, it's not it's the opposite to the Earth. If you imagined a flattened an ellipsoid which was flattened at the equator, like this. It's not working very well like that. If you imagine that thing, and it's rotating around this way, maybe, rotating about a vertical axis, okay? Now, there are also elements within that galaxy which are which are moving in various directions. Let me see. I don't know if there's a computer simulation or if we're just using our imagination, but let's just take his example here. He says, if we assume that the near side was on the left side and the far side on the right 50,000 years ago, for the sake of argument, okay? After 25,000 years, the galaxy is exactly edge on our line of sight. So this thing, which is edge on, is like that. Say it started like that, and 50,000 years later, 25,000 years later, it's edge on, which is actually much thinner. Let's take it like that. Now, let me see what he says then. Then at the present time, which is another 25,000 years further on, the galaxy is tilted the other way around. What was the near side is now on the right, and what was the far side is now on the left. Okay, so it's done it's sort of a revolution. We cannot see the galaxy in any of these positions because, as explained above, during the time taken by light to traverse the distance to the front of the galaxy at O, it will have changed its position. What we observe is a combination of positions of portions of the galaxy at different times on its orbital path. Now, that's what I've been saying. I'm just trying to see, is he explaining it very well here?
Does he have like a picture with like a regular spiral galaxy that he can explain, those? Because I could kind of understand his like the bar galaxy where it has those two little things at the end. But a spiral galaxy, I mean, it almost kind of reminds me of like those wind chime where, well, I don't know, they just have thing and it spins around and it kind of makes a pattern, even though, it's maybe that isn't exactly the right analogy, but I see we got some other people here. I'm wondering, we have.
Yeah, I think Bob Gray says, "Can you hear me?"
We've got Bob Gray's here, Alistair is here. We've got James. Let's add James onto the conversation. So James, have you been keeping up with Ian's hypothesis that the spiral galaxies aren't actually spiral? Let's see. I think we're gonna need to unmute you here. Yeah, you'll have to mute.
You're muted.
You'll have to unmute yourself, James. Can't hear you, James.
Okay, I unmuted my mic. Franklin, your voice level is very, very low compared to Ian's. That's also, I just joined about 3 or 4 minutes ago. I was a little late to join today because I was preparing 2 slides and had to bring them over by a thumb drive to this computer, which pertain to dark matter. It's the perfect vacuum composition paper I'm writing now, and these are the 2 main figures in it. So when you're ready, if Franklin can boost his voice volume, he'd be. Ian is coming in crystal clear, his audio, but Franklin is very, very low. So it's a matter of mixing, I guess.
Well, I changed my mic. Is this any better?
You're still very, very faint.
Still very faint?
Yes, you have been very faint. I didn't want to push it too much, but I did say that at the beginning. You're very faint, Franklin.
Oh, well, if that...
Now, Ian, I can hear crystal clear at the volume setting I have here on my local computer.
And likewise, I can hear you, James.
Well, thank you, sir. Now, I did catch that you were talking about referencing dark matter, but I have to admit that I did miss about the first 25 minutes of today's session because I was on the other computer finishing up the legends to put on these figures. Now, what I have is I can switch to in the two figures I prepared concerning vacuum composition, which pertains to dark matter, okay? In other words, perfect vacuum is not empty space, is my message, that in a nutshell. And I have two figures to show you, should that be appropriate at an appropriate time. I don't want to interrupt Ian's presentation. But, you know, like if that comes up, I have them queued right in my browser here. I just have to click to those two figures. If I can share my screen, and boom, boom, you've got it.
Okay. Well, we were good. Let's see. Is that any better? I kind of tried to switch my input.
No, you're very faint still.
Still very faint.
I bet you Ian would agree, which would mean that it's not my system here. It's what you're transmitting. It's the audio level you're transmitting.
Well, I guess we're going to have to live with it because I don't think there's anything I can change.
See, I can hear that you're saying something, but not exactly what you're saying. Where did Ian go? I don't see him on the screen.
Sorry, I just muted my mic while you were talking there, James. Yeah, I agree. I mean, I thought it was just my system, maybe. I've got my volume turned right up. I think if Franklin could find some way of increasing his volume on the mic, it would help.
Yeah, I'm looking around. Is that any better?
No, it's not.
No,
not yet. I'll give you a shout when you're coming in strong, like Ian's voice is coming in strong and clear.
I mean, you can be heard, but it's very difficult to follow. It's so much easier when you're hearing the volume, you know, nice and loud. As regards what you said earlier, James, I mean, why not show your slides and that's fine. We can look at those. My point, if you missed the essential thesis of what I was saying, I can repeat it and you know, get your view about that. We can do that later. That's fine as well.
Well, either way. Well, let me try to be very brief and present these slides then. What do? I would click share screen.
Yeah, just click share screen.
Okay, just since your audio is low, Franklin, just shout it out. If you raise your voice volume, you know, just shout it out. Then I can hear you. So I'm going to click share screen, and let's see what happens. Share screen. Okay. Now I go to the first slide.
Let's hear it. No, I don't think you've shared the screen yet. We don't see it. You have to click share screen, and then you have to click on the share your whole screen.
Okay, let's go back here. Share screen. Share audio. I want to put that on. And the entire screen.
Yeah. Click on
share.
That.
Okay, I click share, but nothing is happening.
Yeah, you have to click it late. You have to click.
Okay, how about if I click application window?
You could try that, but you have to click on in the dialogue itself, and then below it you have to click OK, I think.
Oh, I see what. Yeah, now that you're right, Franklin. I clicked the icon, and then the share button lit up, and now I'm clicking the share button.
Let's see. You're still not sharing it for some reason.
Now am I sharing it?
For some reason. Let me try this again. So,
Oh, it
share
says
screen.
it's sharing a window, and it says I have the option to stop sharing if I want to.
Let's see. Well, we see your. Let me see. Do I have to add your thing there?
Do you see a figure, a graph?
Okay, now I see the figure. So
Okay,
now I have to go and
if
take
everyone
care of
can
my
see the
mom.
figure, I can
So
describe
I'll let
what
you
we
talk.
have here. What should I start to describe what I have here?
Yeah.
Because
let you
I'm
take
seeing
over
the figure
meeting here
only.
for a
I'm not
moment.
seeing StreamYard at all. Because I'm seeing my own screen. So should I start to describe what we have here?
A very small annoying thing, which maybe some of you have noted, is when you mute your mic, you get a big message, your mic is muted. Now, in this case, it covered part of your graph. So I didn't, I've unmuted my mic because it's obscuring the graph. I don't know if there's any way of getting rid of that message.
Now, I see. Okay, well, if you can hear me, could somebody say something to say, yes, I hear you?
Yes, hear you perfectly.
Okay, Ian, thank you. What we have here is using the Binary Mechanics Lab simulator, which is a free download, by the way. We are doing each point here in the two curves are individual runs where the initial density is varied over the range from absolute vacuum, which is 0 quanta in the simulated volume, 0 one-state bits is what a quanta is, up to the maximum possible, where every bit loci in the simulated volume has a one-state bit, or what I'm calling an energy quanta. Now, I'm just going to go through the legend here. The initial density. What is this? It's the proportion of bit loci in one state, as I just said. The final density now is when the simulator is run in vacuum mode, quanta leaving the simulated volume are simply lost. And so that energy is lost, and we're cooling down to 0 Kelvin, which is defined by 0 quanta radiated from the simulated volume, and by 0 translational particle motion. Particle motion is defined in binary mechanics as quanta moving from one bit cycle to another. Okay, now, excuse me, the particle threshold up here is the nucleon count, which is mostly protons, but some are neutrons, statistically greater than 0. And that's the initial bit density where you start to see that the blue curve is greater than the pink curve. Okay, that's our threshold. Now the particles, this area here between the two curves, what is that? That's the estimated quanta density based upon final electron and nucleon counts. And we could go into how those counts are done. But that's your estimated part density here. Now I have a message here which is covering up the rest of the legend, unfortunately. But perfect vacuum would be the final density minus the particle density. So all of these quanta here, you notice in this region, that's over 20%. Okay, 0.2 of the density of quanta in the simulated volume is perfect vacuum because we've subtracted out the particles, okay, in the final 0 Kelvin cooled state. Now I'm going to go to Oh, the last thing is just as a point of reference in another paper, the observed proton electron mass ratio of about 1,836 was observed roughly at this bit density, which might give you an idea of where we might be in this curve. This is speculative now, in terms of standard pressure and temperature, or what we have in our rooms as we're speaking now. Now I'll go to the second illustration. Okay, we have the same initial density, and this is just showing you that the percent, the percent, excuse me, too much smoking. The percent vacuum curve is the percent of quanta in perfect vacuum, defined as no atoms. We've removed the particles, as shown in the previous illustration. So it's the percent of quanta in perfect vacuum, quote unquote, portion of the final density at 0 Kelvin. And so you see that nearly 90% over this very wide range of the perfect of the total energy is in the perfect vacuum. There's your dark matter. Okay. In other words, most of the energy quanta in any simulation is not the particles. Physics textbooks are going to teach you that this is empty space. And so we're debunking the myth of empty space, whether we're considering even a single atom. They say that most of the volume of an atom, take the hydrogen atom, is empty space. Not true, according to this data. Now, finally, and then I'll be quiet and get some feedback, the percent kinetic is the percent of the initial density lost to, to quanta radiation, in other words, exit from the simulated volume. Now, when you run in vacuum mode, any quanta that exits is just lost. But we can plot what percent of the initial density is lost. And as you can see here, in this range, which might be our room temperature, a rather low percent is lost when it's cooled to absolute zero. But you notice how this curve goes up. This indication of all of these quanta, such a high percent of the initial density leaving the volume, we're talking about an explosion, an incredible expansion. And I will close by going back here. My final thought is this. Notice how the vacuum density is lower in what I'm calling the plasma range, which is defined in the paper called Elementary Particle Energies, and and the lepton quark soup range here. Here we have an incredible explosion, and it is such a violent outward going of quanta from the simulated space that the final density shown here is much lower than what we have up in this peak area here. Even the plasma is a rather explosive, expansive thing if it's not contained, okay? And you notice how that my explanation is that the outward motion of energy quanta from the simulated volume is also great enough to result in a which is significantly lower in this range here. So, message. In other words, what nebulous explosion are these huge explosions that the astronomers talk about? My message here is that if this data can be extrapolated to those astronomical events, there could be areas, and I should have said volumes, vast volumes of the universe which have a much lower vacuum energy density than ordinary room temperature levels seen over in this region. End of story. Now I'm going to stop sharing, or should I keep sharing in case there's comments about the graph? I'll stop sharing.
Just keep that up
Go
there.
and go back to
If you want.
Okay,
We got some other people
that's
here.
what I had to present.
We've got Carl and we've got
Hi,
Jim.
Carl.
Hello, James.
We've got Alistair.
You've gone even lower, dare I say, Franklin, in volume.
Oh, yeah. So you're going to have to just bear with it. There's nothing I can do. So you'll have to discuss amongst yourselves. So we have two hypotheses here. So what do you think of James' hypothesis?
Well, I might just make a brief comment that perhaps we've noted in the past, and I just repeat that, sort of people who deal with the theories of ether, like myself, find this interesting and maybe complementary. We're perhaps looking at things. I mean, the question that the atom is not mostly empty space, but is occupied by some sort of medium. It might be complementary ways of looking at the same phenomenon.
I agree.
That's my initial response, anyway.
And I find that very, very intriguing because looking at the simulator, you see all these quanta there, and you say, well, where are the particles? And in various efforts, which I've published in my journal, I've attempted to systematically define what is a particle and what's not. And when we subtract out what we can call a proton or an electron, there's, as you can see, a huge number of quanta left. And that's our perfect vacuum. By conventional physics definition, perfect vacuum is a very, very busy place. And so what others might be calling the ether would be, in my context, in the context of my work, the binary mechanical model of space and the huge number of energy quanta which it occupies, and which occupies that space. So we're debunking the myth of empty, that perfect vacuum is empty space. As far as I'm concerned, empty space in binary mechanics is absolute vacuum, a volume in which there are 0 one-state bits, what I'm calling zero energy quanta. So yes, there can be some empty space in the binary mechanical model. It's called absolute vacuum. But perfect vacuum, as a matter of fact, most of the energy is in perfect vacuum and not what we're observing in terms of matter, what we're calling matter, atoms. So you see that chemistry only deals with somewhere around 10% of the energy that's in the universe, with chemistry being defined as combinations of atoms, right? If you will.
Let's see here. Can you hear me any better now?
Yes.
Okay, good. I found some settings, so hopefully that'll
You're
fix
up to
my
normal.
microphone problems.
Yeah, it's perfect now.
Okay, excellent, excellent. Okay.
Congratulations, Franklin.
Yeah, I don't know how is it there's like a microphone level and it was like turned way down. Don't know how that happened.
I've noticed
Okay.
that sometimes these Windows updates or other software messes with your settings, and you come back and say, "Well, what happened? I didn't do anything." Oh, yeah, there was a Windows update. Those so and so's.
Okay. Well, now from time to time, I might have to go take care of my mom who's calling me. So, why not Ian, you take over for a little bit, okay? While I go see what my mom's doing.
Right. Okay, that's a little surprise. Well, So there are two things which I suppose we're discussing at the moment. One is James's enunciation of the particles and the contention that we don't have anything that's approximating to empty space. And we've just been talking about how that relates to the ether. Now, the other thing which we were talking about at the beginning was the question of the shapes of galaxies, like in particular the spiral arms of galaxies, and whether these were real in the sense that what we're observing is really, if you look at it, a composite image of different parts of a galaxy which are rotating maybe at very great speeds all over the place, and we're seeing at different times different parts. So really, if we see an object which is, say, X light years away from us, we're seeing the light that emanated from that X light years away. If it emanated at a greater time in the past, well, then the light has passed us already, so we don't see it. And if it emanated at a more recent time, the light hasn't yet reached us. So I suppose, apart from discussing the geometry of the galaxies and maybe the contention that the spiral arms are really apparent, one might say that this is one of the points, I suppose, where mainstream might postulate a dark matter, because they're seeing gravitational effects and they're not actually seeing any visible entity, in that area. Simply, I mean, it's a very simple thing. Simply because the light either hasn't reached us yet or has bypassed us. Jim actually was sending me an email there about it, and I was actually going to reply, but perhaps I could just, as I'm talking, I'll just delete what I was going to say. Actually, I don't think I'm able to. Or, backspace. Yeah. So I think Jim was saying that, are you aware of any studies that compare the density of dark matter to the magnitude of the local gravitational potential? And I was saying, well, presumably, Jim, you mean the mainstream definition of the density, what they would say the density is. If so, I'm not quite aware of any studies that they claim would relate their density to the gravitational potential. But you then say, what do I think of the concept that dark matter is the ether? Yeah, I think I've come across that. I think maybe you've mentioned it before. I'm a little skeptical about that, because I think, first of all, dark matter has been introduced as an ad hoc hypothesis just to save existing theories. To save theories like general relativity and the expansion of the universe, and they're also explaining the so-called anomalous rotation of the arms of the spiral galaxies as you go further out, and they just say dark matter, 96% of the universe is dark matter. But I think that's just an ad hoc hypothesis. Now, I think dark matter, to a certain extent, I don't like the term actually, because I think it's just an invention, but dark matter can be something for which there's a gravitational or electrostatic even effect, but for which we cannot see the object for the reasons I've given a moment ago. So that could be the sort of the dark matter between the interstices of maybe a nebular object. There may be effects, but we cannot see. Everything is dark. So it's just that the object hasn't actually emitted light at the same time in years ago as the distance in light years from us that it is. Now the ether, I don't know. I mean, maybe just to get further on Jim's point, maybe some effects have been noted which really should be attributed to the ether, but because the ether, or non-empty space, if you like, to follow James's discussion there, is a sort of a verboten element now that you're not meant to believe that, and hold your job in a well-paid establishment. So it's a concept which is not acceptable. People might talk about dark matter. So in that sense, Jim, maybe it's been confused to a certain extent. But I don't personally at the moment anyway. I'm open to it. But personally, I don't like at the moment just saying, "Oh, dark matter is ether," and that's the end of it. But some of you would maybe like to come back upon that.
Yeah, I have a question for Ian and any of the others as well. I've been sort of confused, to be honest, by this whole definition of dark matter, not to mention dark energy. And it seems that, is it not true? It seems that physicists are, in the mainstream of physics, are not being precise in their definitions. Isn't a hydrogen atom or helium or other atoms at their base ground state dark? That's either yes or no.
The thing is that what they mean by dark is that they basically don't know what the heck it is. I mean, there's been some emails, and I think the best description is that we have the calculations for what we think the matter, or that the observable matter, what it should do, and then we have according to the equations, and then we have what it actually does. And,
okay, but that doesn't answer the question, Franklin.
Well, the thing is that they don't know what dark matter is.
Is an atom in the ground state dark?
Is not dark,
emitting any light? That's a yes or a no.
No, that's it. They're not dark because we can observe those hydrogen and helium atoms because they are part of suns, and we can count the mass that's we can visibly see. So
that doesn't make any sense to me, because if a hydrogen atom or any other atom is in its ground state, it by definition is not emitting light, and you're definitely not going to see it.
Well, I'm thinking that
now we have multi-million.
Is that there isn't that much that's dark, that's in the ground state. Now that
in the vastness of space, and the vastness of outer space, Ian's talking about galaxies, where it's almost 0 Kelvin temperature according to the cosmic microwave background information. I would think there would be that, in fact, maybe even most of the hydrogen atoms in the entire universe are in their ground state.
I mean, that couldn't be.
And so you're saying, well, it's only a hydrogen atom because I can see it because it's in the sun, or it's not in its ground state. It's received a photon and now it's emitting a photon to go back to its ground state, and therefore it's visible matter. But in other words, I find a great deal of imprecision in mainstream physics descriptions that I've read as to dark matter, and in fact there are multi-million-dollar proposals postulating the existence of a dark matter particle and attempts to find it and define it. And so you know, what about all of the atoms in the universe that are in the ground state?
Well, fundamentally,
they're dark.
Fundamentally, my position is that where we observe maybe effects in the cosmos and cannot see any visible objects, that is my position would be that that is caused by particles of the same nature as we view in the laboratory. So in other words, it could be hydrogen or helium in the ground state. It could be other gases.
Oh, good.
Yeah, so I do accept that, but that's my fundamental.
And remember, I'm asking a question. I'm not making a huge assertion.
Yeah.
I'm making what I think sounds logical. But I have a question: is why does what I'm saying that sounds logical to me is not even mentioned?
No,
because not even mentioned ground state atoms.
is they have quite the contrary position. They would say that 96% or whatever it is of the universe is composed of this postulated entity, which they call dark matter, which is not homologous with what we view in the laboratory. It's some other animal altogether, and we don't know what it is yet, and we're searching for it. And hence, we have large sums of money being devoted to finding a new particle, dark matter particle, or God knows what. That's their position. They've postulated some completely new entity, but I don't think there's any.
Listen carefully. Eon was just cited, and about 90% is our dark matter of and I just presented slides showing that perfect vacuum consists of 90% of the density is energy quanta, these one-state bits. So I'm right on the same wavelength, so I'm trumpeting my work that I just presented, and I'm writing the paper now. First I make the figures and then I write the paper. That not only is empty space a myth, unless you want to consider particular bit loci, which have zero states and therefore are called absolute vacuum. So yes, those are quote unquote empty space, if you will. But actually 90% of it is actually energy quanta. And so so not only am I contradicting the idea that there is empty space to any great degree, but that in fact most of this missing matter is right there in the graph I showed you.
Well, I think that might be something that's a little different than what mainstream is saying, because they are saying that the dark matter congregates around the real matter, right? Now, you're just saying that the background matter is extremely dense, which I would agree with, but that wouldn't explain why it would be denser around, say, just the galaxies, because I think that they're
how about gravity?
Sure how they map this stuff out, but they have these maps.
Well, and that's a gravity-like effect. Quanta attract other quanta.
Perhaps
the baryogenesis phenomena is a major gravity-like effect where
it may be,
quanta are collected and concentrated by baryogenesis.
But as your fellow etherist, though, I would say that the ether is pervasive even in areas where we don't observe any observable matter, and it would be almost as dense. So the problem is,
that's what my graph shows,
which is uniformly distributed, then it's almost like it's not there because it pulls in every direction evenly.
Well, the graph shows that perfect vacuum. Pick any place in outer space you want and look at perfect vacuum. It's teeming with quanta.
Yeah, it's teeming with quanta. That doesn't explain why it would be more teeming in where there's other matter. I mean, an interesting observation.
Well, that goes back to a discussion of gravity-like effects.
Well, an interesting observation that might be
relevant here.
Step by step. You should understand this, is that some other people have done some studies about whether you can predict how the galaxy forms, basically, and you can do it by just looking at the observed, bright matter. So I'm not 100% sure how they did this, but the crux of it is that in order to predict the galaxy curves accurately, you need only look at the visible matter in the universe. There's some way of calculating it so that no matter what the shape of the thing is, it comes up with the correct shape, which to me says that, dark matter, because I've seen it, it's like they say it's been in halos, or it's some cloud around in some area. That says that all of those particular hypotheses don't necessarily need to be true. If the only thing you need to do is just observe the visible mass, then there does not need to be any other dark matter particle. I mean, the thing that brought this up is that the people who are spending the billions of dollars to look for the WIMPs, these massive particles, which only interact by gravity and are supposed to account for the mass required to keep the galaxies in line, that their searches have just basically failed. I mean, and they've searched so much that basically all of their favorite candidates are no longer valid, is the problem there. So,
and I would cite that result, Franklin, as in support of my work. That there are no WIMPs.
Yeah, there are no WIMPs.
That I'm describing, but there are no WIMPs out there.
I think this is the problem. They've done enough experiments and spent enough money that they have to say that they're not there. They're kind of coming to that conclusion. And that's what's causing crisis.
Very supportive of my work. Yep.
Now,
as a matter of fact, I've even cited that.
This whole ether versus galaxy things. I made this point in one of my emails, in that, some people think that the dark matter is the ether, and that accounts for the extra matter needed to account for the spiral galaxy distribution. So that's one way to go. I would personally disagree with that. I would say that the background ether is dark matter in the sense that we don't recognize it, and it's pervasive, and it comprises like 90% of the actual matter in the universe. I think we would all agree with that, but I don't think it contributes to the spiral galaxy distribution thing. I think what we really need to do is that if there is not actually a dark matter, particle in the sense that it adds gravity to the system, then you have to just go to the other alternative explanation, which is that you don't understand how gravity works. And I would be more in favor of the idea that the reason why galaxies do the things they do is that because we just don't understand how gravity works well enough. Because right now we think gravity is just a simple 1/r² attractive force that's working against the centrifugal force, and that balances out, and that causes orbits, right? That's the simple, naive picture that we're looking at, which doesn't seem to work when you apply it to galaxies. You get that just doesn't seem to work. Now, considering that we really don't understand how gravity works, mainstream, is like, still have really no clue on how that works. I would say that is still a much better candidate than thinking that there is actually some particle that has gravity that's causing a larger gravitational force to appear in our galaxies than we would expect, right?
Now, Jim Marson has been typing some comments here, which are in agreement with my work. The last one, maybe Jim could just speak up. And if you postulate that the speed of light is a function of density, I not only have postulated that, but my work shows that, demonstrates that. It explains gravitational lensing. Well, of course. I wish Jim would just speak up. He's making all these comments here in the private chat. And
yeah, I would actually agree with that as well. That there is an ether. The ether has variable density, and that variable density is just a refractive effect, and that explains gravitational lensing. But my argument is that doesn't explain the galaxy rotational curves.
Well, Vera Rubin, in her papers in the 70s, who was credited with describing the rotational function of the galaxy, stars in galaxies. Essentially, one of her curves, as I recall, showed that it was consistent with some kind of decrease in the effective mass with distance that's also a function of the inverse of radius from the center of the galaxy, which is the same as gravitational potential. So that does, at least for galactic rotation curves, that does match up.
Well, I think that's in the camp of the modified gravity.
No. It was just explaining or describing essentially how the rotation curves, the rotational speed of stars in the outside of galaxies decrease more slowly than would be expected, and showed that it was consistent with the mass distribution of 1/r.
Okay, yeah, that's another possible.
She wasn't trying to explain whether it was some modified gravity or what. She's just saying that this is how it changes. This is the missing matter distribution.
Yeah, because I've always wondered about that myself, because you think geometrically the matter that's way out in the edge of the galaxy has to be influenced by like all the stuff that comes before it, but the 1/r² gravity formula just completely ignores all of that. It presumes that all of the mass is concentrated in the very center in a speck, right? That's what it basically presumes. It doesn't. And they're allowed to do that because I think the calculus of how you do gravitational calculation says that you can do that. So like you can calculate the force on me on the Earth, and what you need to do, instead of adding up all the forces of like the rocks that like 3 feet under me and 100 feet under, and then like 3 million miles, what you can do is you can pretend that all the mass of the Earth is concentrated in the center of the Earth in one spot, and you get the same answer.
It's equivalent, right? That's what Newton showed.
That's what Newton showed. But the thing is that I kind of question that. It's like when you get to something that may work for something like Earth, where it's relatively solid and the mass is next to you and blah blah blah. But when you're dealing with something which is like shaped like a frisbee, is disc-like, you've got. So the mass is not distributed evenly. It may just simply be that that 1/r². You can't use that calculus trick. The Newton's calculus trick.
1/r². I'm saying 1/r. Gravitational potential, not gravitational force.
So what you're saying, that gravity is actually a 1/r force?
Gravitational potential is different than gravitational force.
So the solution there is that gravity actually ends up being a 1/r force
squared. 1/r, that's gravitational potential. And then if you take the gradient of that, you get gravitational force, and that's 1/r².
But you're suggesting the hypothesis is that gravity is not 1/r². It's actually the effective force is 1/r.
Gravitational potential does not generate a force itself. It's the difference in gravitational potential with the distance that generates the force.
Or the difference in gravitational force would give you a potential. It's another way of looking at it.
I mean, the other weird thing that we have to think about is things like Bode's law, where basically you find a stable planetary orbits approximately twice as far as the previous planet, which, that seems to be a kind of interesting progression. And it doesn't seem to matter what the mass of the actual planet is. whether it's Saturn, which is gigantic, or Mercury, which is tiny, the planets seem to occupy those particular slots where you've got one planet and then twice as much distance away you got another planet, and then twice as much distance as that you got another planet, and twice as much distance as that you've got another planet. So and certainly a simple 1/r² force wouldn't do that.
That's true in regards to Bode's law, but the larger planets tend to be concentrated in the center. You have a sort of like a cigar shape. It's large in the center. The smaller planets are nearer the sun and further from the sun.
I guess that would be true. I mean, we do see that. Well, I think we see quantization, that same kind of quantization of just like the moons around Jupiter or Saturn or something like that. We see the quantization even on, say, a galactic scale, it seems.
See, one thing we might look at some stage, I don't know, maybe some other day, is not so much quantization, but sort of certain arithmetic patterns in nature which are adopted for various reasons, and you can look into them. I mean, things like, the golden section, and things like the ratio of the sides of pineapple scales, and the marks on turtle shells, and things like that. It seems to be sort of an optimum type of ratio. And I think perhaps Bode's law would be similar to that, because it's related to the Fibonacci series, as far as I recollect, which also the golden section is. You can derive it. I think it's quite a general law of nature, actually.
All right, looks like we've got some
minimum energy usage and so on.
Looks like we've got some comments from Facebook and YouTube here. Let's go over a couple of these. Let's see here. So it says, my concept of galaxy formation is that chunks move towards each other and yet never hit straight on due to the original trajectories. Therefore, they must swirl as they approach. Okay, that's a possibility. I mean, I did mention that, the galaxies kind of look like what you see when you pull a drain from your bathtub, and it kind of swirls in. It looks like a little tornado kind of thing. And let's see, here's another comment from Han. It said, even atoms near 0 Kelvin can get excited by photons, and after that, they can release that photon again. Dark matter does not react on photons. Well, I would be presuming we know what dark matter is. It's kind of hard to say what the properties of dark matter are when you don't know what it is. That's kind of frustrating, isn't it? It's like they postulated what it could be, and this is, like I said, is the crisis, and they can't find those things. But once again,
well, it looks like they're ignoring all of the atoms that are in the universe in the ground state, which would qualify as dark matter, i.e. they would have a gravitational effect, but not be visible. They're just simply ignoring that and just saying, well, there must be something else.
Yeah, I think it could be. It could just be a lot of dust, right?
Well, that's matter in the ground state.
I'm not reluctant to use the term dark matter, because it's been defined by the mainstream. It's a bit like Humpty Dumpty. When I use a word, it means exactly what I wish to mean, nothing more and nothing less. And it's sort of like a postulated otherness out there that we don't know anything about, and we'll know something about it in the future. But it's unlike anything that we consider to be ordinary matter. And therefore, if I say, if you say, well, certain effects are caused by what they think is dark matter, you're sort of using their term. And I normally try to steer clear of that, because I think it's fraught with difficulty.
Yep. But this is the thing, is that the theorists have come up with, they think, is a findable particle. They figured that if that particle exists, then it must decay. And if we build a super expensive experiment buried 100 miles into the ground, we should be able to find it. And then they're just a little bit embarrassed about, well, we don't find anything. Is the problem.
If I may, if dark matter is involves atoms in the ground state, you can't write a grant trying to find something and get millions and millions of dollars for salaries of hundreds or even thousands of people around the earth. So you must postulate. I'm being sarcastic, following up on what Franklin just said.
Yeah, it could be. It's not profitable to find space dust, right?
Exactly. All right. Yes.
So
Yeah, I'm being equally cynical. I was going to say that I would predict that they actually will find a particle, having spent so much money on it, and there'll be a big announcement to that effect, because that's what they have to do, and they'll do it some way, by hook or by crook.
Yeah, just like they found the Higgs particle, right? They
Yeah,
had
I
to
was
find it,
thinking
right?
of that. Yes.
It's like you look at the curve; it's like perfectly normal, except for the tiny little bump. I say, "Oh, there it is." Okay, you found it. Thank God. Okay.
well, maybe the reason they can't find it is because it's the media. It is the ether.
It could be.
And the ether.
Or as I would say, it
Not a-
could be atoms in the ground state, but probably most of dark matter is the quanta in perfect vacuum.
Well, that could be. Well,
90% figure pops up, just like in the graph I showed earlier.
But dark matter is postulated for a number of reasons, I suppose, and they might be quite disparate. I mean, I suppose where they can't see anything optically, and there are some effects, they're saying, oh, well, there's dark matter there. But they're also postulating it to explain what they need to introduce with regard to the theory of the expansion of the universe and things like accelerated expansion and expansion rates. So it's sort of like a bit of a catch-all. And I suppose with dark energy, it's a catch-all. It's explaining all that.
now dark energy is supposed to explain why the galaxy appears to be exploding. I mean, not only is it expanding, but it is rapidly accelerating outwards, right?
And that's because they have adopted a sort of a Hubble linear relationship, between their so-called velocity of recession and the redshift, or if you like, between the redshift and distance. But I mean, that linear approximation would only apply, in my view, for very small elements of the curve. It's actually incorrect. It's more of an exponential curve, actually, if you calculate it. I've done that based on Maxwell's equations. So, that they adopt a linear curve, and then when they find it isn't linear, they say it's actually expanding even further. So we'll postulate a force, a demon. It's like Maxwell's demon, a demon. Let's call it dark matter, which is influencing that.
Yeah, the other weird thing is that with the dark energy things, that they equate that to matter, and then they add that to the matter equation, and then reduce the amount of matter that's physical, like us, to like 1% or something like that. So that like 99% of everything is dark matter and dark energy, which seems absurd on the face of it.
Well,
But,
the entire light would certainly explain the velocity not velocity, the redshift with distance, but that was rejected because nobody could come up with a physical mechanism for it. But by rejecting that, they've invented all sorts of even crazier or inflation to account for their standard model.
Yeah, I would say that if it were up to me, I would just kind of accept that as a physical law, that you get that redshift, and that it just happens, but it's not due to actual recessional speed. That empirically, that's what we seem to measure, right? It's so I think that's the way we should take it. But you have to make some assumptions, right? You have to, first of all, assume a constant universe. And then based on that, then you would have to presume that it's just the redshift is just a function of distance. But
it follows other laws of nature which don't allow transmission of energy without dissipation. So it's merely another.
Yeah, I would say that that's true too. That how is it a beam of light can travel like billions and billions of years and not suffer any degradation, right?
And if
I
there's,
say they do.
if there's an ether, then you've got a physical medium that can account for the dissipation.
I personally think that I think we could do the experiment where we should be able to send frequencies to our Pioneer space probes, and we should show that even the Pioneer space probes exhibit that same redshift. But we know the exact speeds that these probes are receding away from us, and we could then directly say that it is just a measure of distance, rather than a matter of speed, since our probes are going at a constant speed away from us, that we're pretty sure we know what that is. But I don't know whether we have the necessary precision to measure that redshift, or maybe that could have something to do with the Pioneer anomaly with the blue and redshift. Although I think it works in the opposite direction that it should, but I think that should be directly measurable. You could either say that is a real effect, or that it's actually due to recessional speeds, I would say. But we got another comment here from Count von Bruno, I think kind of agreeing with that, that the ether is much more dense than the matter. As James would say, that the ether actually predominates, really. I would say that the ether is actually the densest substance in the universe, and that when stuff like us is actually a contaminant in there, and that regions that have us in it actually make space less dense, is what's going on. And one interesting observation we see in the universe is that it's not evenly distributed. And he mentions that matter is like air bubbles, but if you look at the overall structure of the galaxies, they seem to be on the edge of bubbles. It's like the galaxies are the soap bubbles themselves. And that if we look inside of those bubbles, we find absolutely nothing, just nothing, not a single atom in there. And I would say that's because those are regions of pure, unadulterated ether, and they want to clump together because they're the most densest thing. And all of the crap, which is the visible matter, is being essentially pushed out as far away from the concentrations of the pure ether as possible. So I would say that as a hypothesis, that kind of explains what that overall galactic structure is, and why we don't see not a star inside these bubbles. I mean, there's like nothing. You'd think there'd be something, but no, they're completely blank. Apparently, only like the bubble-like surface. It actually contains the visible matter. Okay, so I'll let you guys continue the discussion. I've got to go see what my mom wants.
Did I understand correctly that people are postulating that the mass of stars and objects at the perimeter of a galaxy is less than, or perhaps is reduced, which would then explain some astronomical phenomena? Did I understand that correctly?
I didn't grasp that. Did somebody say that?
I must have misunderstood. I think people were trying to explain something about an anomaly with regard to the most peripheral parts of spirals.
Yeah, the speed.
What might be expected. The speed, okay.
Yeah.
Well, that would pertain to mass. Would it not? Well, basically, I'm sort of out of my league when it comes to astronomy, but let me throw this out, and those who know more about astronomy, it might make some sense. If we say that the inner parts of a galaxy, the inner volumes of the galaxy, are radiating quanta toward the outside, it would mean that the quanta density at the periphery of a galaxy is less than closer to the center of a galaxy. If we can accept that, my second point is that my simulation experiments have shown that as quanta density decreases, so does proton or nucleon mass. So we can then say, if that result in little tiny simulation experiments can be extrapolated to whole galaxies, if the bit density or quanta density at the extremities or periphery of a galaxy is less than toward the center, much like light intensity is greater near the sun than further from the sun, then the mass of these objects at the periphery would be less. Correspondingly, as you get higher bit density, the mass increases. That's what my work shows just in the laboratory simulation. I don't know whether that can be applied to whole galaxies or not. I guess I just don't have the astrophysical knowledge to work with that. You know.
I mean, presumably they observe similar masses at different positions in the galaxy, near the center and further out. They observe similar masses, and they find apparently that the masses further out are actually rotating at a greater rate than would be predicted by Newton's laws.
Well, if it's a greater rate, then we're talking about the mass could be actually less.
Indeed, I mean this could come into the equation quite possibly. It's an interesting theory. I'm just saying that I think the conventional astronomy would say, well, they've eliminated that. I don't know, I'm speaking for them, and I ought not to do that, but they'd probably say we've eliminated that because we've got similar masses. We've analyzed those, but I mean, these are certainly parameters that I think will have to be put into the equation. I mean, my whole concept of the galaxy, which I started talking, really indicates that it's not quite as simple as this at all, because we're looking at an object in 2 dimensions, flat on, which is actually moving in 3 dimensions, and furthermore, the whole unit is rotating, let's say, but the elements in it are also moving all over the place. I think it's something I started looking at Kelly's book here. I think he simulated this by getting a balloon. Let's see what he said. He said the derivation of the shapes required a 3-dimensional exercise, which was carried out by rotating and viewing from a fixed position an inflated balloon with the galaxy drawn on its surface. So you had to allow for that, and you got well, he claims you got the vestiges of a spiral arms. You got sort of these circular rings, there, and then he said because of the cutoff point, you have various cutoff points in these arms, depending upon when the element was at the right distance for us to view it, that the light hadn't passed us already, or the light hadn't not reached us already. So if you take in these little rings with the cutoff points, you get that diagram there, which is a spiral galaxy. But it's actually just originally an elliptical galaxy, which is moving in a vertical axis relative to the observer, and what we see is that. Anyway, that's the theory. So I think that the bottom line is that what they're doing in the mainstream is they're just observing things, and they're getting quick fixes. They're inventing things to say, oh, well, we understand that now. We explain it. It's dark matter. Or it's There are no other comments, are there? Here. I mean, one other thing is we can look at properties of the ether, and we're quite conversant with the electromagnetic properties, the electrical permittivity and the magnetic permeability. Perhaps we're not so conversant with other properties, but they do exist, like the conductivity of the ether, which is probably very, very small, but it can be estimated. Based on actually what Jim mentioned earlier, sort of a tired light dissipation system and our observation of the redshift, and you can calculate. Monty has done this first, and I've followed up on that as well. Conductivity of the ether. So I'm wondering if people are looking at dark matter, does that have any properties apart from mass? I mean, presumably they look at mass, but do they look at the conductivity of the field within that dark matter? Do they look at gravitational potential? Does that follow a simple 1/r system as for conventional matter? I suppose they would say we don't know. We just know that this exists, but we don't know really what its properties are. It's really rather suspicious, the whole system. It's really, as I say, an ad hoc hypothesis, a quick fix.
Ian, would you say that the permeability and permittivity would vary with this density difference or the light speed difference?
Yeah, I think maybe we've talked briefly about this before, Jim. I dare say it would. I mean,
which property?
Well, either or both. I suppose in a non-magnetic area, it might be mainly the permittivity, but it could be either or both. And furthermore, well, the conductivity, I suppose, doesn't basically determine the speed of light. It's the electrical properties, except the electromagnetic nature of the wave. But that does affect the dissipation rate. So
yeah, I think that's a great finding on your part.
Thank you. I don't know if Franklin is back. I thought I saw some movement there.
Just a moment there.
Yeah. I hope everything's all right at home there. Yeah.
Yeah. No, it's okay.
Okay.
Are you guys doing okay?
Well, I don't know. You've put us into the deep end, and we're discussing a number of items, but it's a bit unstructured because we're moving from one thing to the other. I moved back to this galaxy business. I think in your absence, I was saying that Kelly was saying that one of the problems is we're viewing in 2D a three-dimensional object which is rotating and whose elements are furthermore moving in all different directions. And in order to see what was happening, he had to get a balloon. Well, Franklin, I think, has left, and I've explained this already to you.
But wouldn't after millions of years the light emission kind of even out?
Even out. Well, first of all, in very rough figures, if I can recollect, I think my calculations indicated that the light dissipation would reduce to 1/e times its initial value. So like a third after 10 to the power of 10 light years. I think that was the very basic round figures. So it's a very, very small dissipation, actually, relative to, say, water waves or sound waves in a gas. Very, very small. But it isn't zero. It isn't non-negligible. The main thing is maybe...
Would it
even out
for usually when they're talking about tired light, they say, well, they dismiss it because it would cause blurring.
Yeah.
Or
Okay.
the dispersion would be different for different frequencies.
Well, I don't know. They seem to have introduced a lot. We could deal with those, but they seem to have introduced a lot of objections to tired light. Even the term might be a bit pejorative, actually.
Oh, definitely.
Yeah, I mean, Big Bang was pejorative, but that's become now acceptable and more science. But tired light is a no-no. That's negative.
Yeah, right.
And I don't know. I think again. I doubt whether some of these objections are real. I mean, you were talking about a physical means of by which it would happen. Now they're talking about blurring and different. Well, I mean, we get different refractions from different wavelengths and so on.
And where does the energy go?
Where does the energy go? Yes. Well, I mean, I always look at the analogy. If you have a dissipation of a water wave, I suppose it's going into the water, and I suppose it's dissipated in heat and God knows what. And similarly for sound, I suppose because you have a vibration of the molecule. Well, in light, you're having to try to on the spot just look at the analogy further. You're having an electromagnetic dissipation in a medium, and whether
it's the CMB,
some other form of energy transmission, I don't know.
maybe it's the CMB.
That's true. That's true. And actually, I think that is central, Jim. I do think that is central to the whole question.
The temperature of space.
Yeah. And I mean, they're all saying, oh, we predict 2.7 Kelvin and all this sort of thing. You know, the predictions based on their expansion theories were sort of like 10 or 20 or 40 Kelvin. And, they've reduced them in accordance with the experimental evidence. But there's no problem really why it should be just above absolute zero. I think if you're looking at a dissipation system where over vast distances in space, you're getting a very small dissipation. As you point out, you're getting a CMB, which, apart from being a remnant of a Big Bang, perhaps is a remnant of continuously dissipative waves. Yes, let's put it that way.
I think that's what Eddington calculated. It's coming from starlight.
Yeah, I think you're probably right, and it got a bit out of fashion, because Eddington also mentioned about the gravitational interaction having a very, very large speed. I mean, this is quite early on, and he mentions the instability of planetary orbits where this not the case. If you had a gravitational aberration, just as we have light aberration, but then when he embraced the theory of relativity, all those things were forgotten.
That's why I don't like special relativity, for one thing.
Yeah, because it planters a lot of those concepts.
Yeah, I mean, if you Eric Lerner, have you heard of him? He showed that the size of and surface brightness of distant galaxies was more consistent with a steady state, a non-expanding universe.
Yeah, I've heard of that. I'm not sure of the name, but I have heard of that being claimed. Indeed, yes.
I can send you a link to his papers.
Yeah, thanks very much. Yeah. Yes, it's strange if we're just a few people wandering in the wilderness and asking fundamental questions. Nobody else is. I don't know about that.
Yeah, it's.
Although when I gave this little presentation on the 1919 eclipse to my little scientific group a couple of weeks ago here, or last month, I just started the paper by saying, you may be aware that I belong to this small but increasing group of what might be termed dissident physicists. And I just told them about the CNPS and these Saturday conferences and so on. So questions are beginning to be asked. But I think in any orthodoxy or in any discipline, people, the expositors of the theory, they always say, oh, we're open to modification and just give us the evidence and so on. But they never like to say, this is tentative and this is provisional. They're always saying, oh, in the 1950s or in the 1980s, we thought that and we thought that's true. But now we know that's untrue. Now we know it's this. They don't like to say that it's provisional. In another 20 or 30 years, it could be completely set on its heels.
So what group is that you were talking?
That group. Well, it's a bit of an interesting thing. I'll just be brief. There's a group called the Dublin Scientific Club, which was actually founded in 1868. It's a really bit of an unknown quantity, a bit of a secret society. It was originally formed as an adjunct to the Royal Dublin Society. And what they used to do, there were quite some eminent members of it, people like Stoney and Fitzgerald, but they used to meet on the third Tuesday of the month, and they would have a lecture, maybe in the Royal Dublin Society, which is now the Parliament here, actually, in Leinster House, but that was the Royal Dublin Society. They'd meet there, and then they would go for dinner afterwards in the Shelburne Hotel. Now, it's just a small group which has existed, for 150 years, but it's not associated with the Royal Dublin Society now. It stopped that maybe in the 1920s, and it became really just a bit of a dining club, a social club. Now, I was invited to join in 1981 by one of my colleagues who thought I was, interested in science. It's this group of people. They're only about 35 members, actually. It's quite small. But we're all fundamentally interested in science. And we have talks. Now, I've given a number of talks to them. I gave... I've given it on things like stellar aberration, and I gave it on my talk on my paper on electromagnetic waves. But last month, I offered to give them a talk on the 1919 eclipse, and did it prove anything? I don't know if you were at the teleconference we had here on the 8th of June. Yeah, it's recorded.
So,
were you there, Jim?
when you did it for the CNPS, yes.
Yeah, you were. Okay, but I think James possibly wasn't there. But anyway, we had it on the. Well, the origin of that was basically there was it was the 29th of May, 1919. So on the centenary of that, on the eve of the centenary, in other words, on the 28th of May, there was a program on one of our local stations here where they interviewed a Professor Peter Coles, who just gave the normal view that it proved Einstein right, and as if like Newton didn't predict any bending and Einstein predict bending, and the tolerances were so great we proved exactly to within experimental error that general relativity was true. So I said we might have a teleconference. So hence we had the teleconference on the 6th of June. But I offered to give a talk to this club, and now unfortunately a lot of them are like myself now, rather getting on in age and retired. But we come from various aspects. There are some physical scientists, not many, maybe some chemists, some biological people, and so on, agricultural people and statisticians. But I expected actually to be to experience some hostility, as what one might do if one questions the fundamental basis of the whole of GRT and the orthodoxy of the 1919 eclipse. But actually, I was quite pleasantly surprised. I was I encountered some quite open response. I mean, people might have said, well, we don't know about this now, we'd have to look into it or something, or what you say is interesting. One guy just joked, he said, if I was right, they'd have to rewrite all the textbooks. I took that as a compliment. But they weren't hostile to me by any means. But they are, in general, mainstream scientists. They're not dissidents. I'm probably the only dissident there.
Okay, well, I'm back here. It seems I think we have reached the end of our 2 hours. So I'm going to wrap things up. So it seems that our main discussion was around the existence of dark matter and how we could explain that. It's interesting. Ian thinks that we're just misobserving the galactic speeds, perhaps because of this an optical illusion. It's interesting. James is suggesting that most of the matter in the universe is, in fact, this background, ether stuff, which I would kind of agree with. Or it could be that we just don't understand how gravity works and that there is no actual matter behind this whole thing. And that gravity is just stranger than we thought. But that will do it for this week's chat. And we'll see what happens next week. All right. So that'll do it for today, this week.
Thank you.
Thank you.
Thank